Okay, in the last video, we were using the calculator to find the output values for trig functions for different angles. But the question remains, can we calculate the exact value of trig functions by hand? Turns out, for a lot of angles, not really. Calculating the value, like the output of a trig function by hand, is in general not something we do. But for certain angles, it can be done. So for certain special angles, we can figure out the exact output values of trig functions. And so we're going to look at two special triangles, which are known by their angles in degrees: the 45-45-90 triangle and the 30-60-90 triangle. Okay, so for these, we're going to figure out what all the side lengths are, and therefore be able to figure out the tangent, sine, and cosine values for any of the angles you see here. 45 degrees, 90 degrees, 30 degrees, 60 degrees, all of those angles. And then in future videos, we're going to take that and translate that into other quadrants in the Cartesian coordinate plane and figure out a bunch of different angles that are sort of related to these ones. So this is going to be our geometric foundation for calculating exact values for certain trigonometric functions for certain angles. Okay, so let's start with the 45-45-90 triangle. So let's draw one of those. In a 45-45-90 triangle, we have, of course, our 90-degree angle here, and then we have the other two angles both equal to 45 degrees. Now, if that's the case, then this triangle is symmetrical, because these angles are the same. So that means whatever length this base is, let's say that's of length x. The other leg of the triangle also has to be length x, okay? That's just based on the symmetry of this triangle. Now the hypotenuse, on the other hand, is going to be a different length. So I'm going to label that with c. And let's take as a reminder the Pythagorean theorem, which says in a right triangle with legs a and b and hypotenuse c, a squared plus b squared equals c squared. We're going to use this for both of these examples. So now, with this setup, legs of length x and hypotenuse of length c, the Pythagorean theorem is going to give us x squared plus x squared equals c squared. So that's 2x squared equals c squared. And what is the c value going to be? Take the square root of both sides, and you're going to get c is the square root of 2 times x. Because when we take the square root of x squared, we're going to get x. Now, I know that normally, I taught you back in like chapter 2 or something, I taught you back a long time ago that the square root of x squared is the absolute value of x. But for triangles and lengths of sides, x is only ever going to be a positive number. So we don't have to worry about negative values of x for this application. So we have the square root of 2 times x. Now we can use that to help us calculate all the trig values. Let's take sine. We're going to calculate sine and cosine and tangent of 45 degrees. So sine of 45 degrees, what does that equal to? That, sine of 45 is going to be, it doesn't matter which of these we look at, it's going to be opposite over hypotenuse, which is x over c, which in this case is going to be x over the square root of 2 times x. And the x's cancel out, and we get 1 over the square root of 2, which can otherwise be written as the square root of 2 divided by 2. And that is the exact value of the sine of 45 degrees. All right, cosine of 45 degrees is the same, because for 45, adjacent is also x. So that's exactly the same thing, 1 over root 2, or in other words, square root of 2 over 2. This is the reason we write it as square root of 2 over 2 instead, is because sometimes we like to rationalize denominators. So that's the standard way to write it. Now the tangent of 45 degrees, given one of these angles, opposite over adjacent is going to be x over x, which is 1. And there you go. Tangent of 45 degrees equals 1. Those values, we're going to talk about those in terms of the radian equivalents later, so let's just leave it at that for now. Okay, so these establish exact values for some trig functions of 45 degrees. Next, let's look at a different triangle. 30, 60, 90. Except instead of starting with a 30, 60, 90 triangle, what I'm going to do instead is start with an equilateral triangle. An equilateral triangle is a triangle where all three sides are the same length. So I'm going to label all sides as length x. Now, if all sides are the same length, it has to be radially symmetric or rotationally symmetric. So if you rotate it and make it line up with itself again, then it must be the same triangle, which means all three of these angles have to be equal to each other. Now, the angles of a triangle always have to add up to 180. So if you take 180 and divide by 3, then you can conclude that all angles of this triangle are 60 degrees. Okay, now what we're going to do is cut this triangle in half down the middle. Straight down the middle here to make a right angle at the bottom, like that. So now one of our, if you look at the purple triangle, one of those angles is 90 degrees. This angle is still 60 degrees, but this angle at the top, since we cut the triangle perfectly in half to make that 90-degree angle, this angle will be exactly half of 60, which is 30. And those 30 plus 60 plus 90 do add up to 180. So there's our 30, 60, 90 triangle. But what we get out of this is we discover that this side of the triangle here is of length x over 2, because we cut our equilateral exactly in half down the middle. So we still have the hypotenuse of this triangle is of length x, but one of the legs is of length x over 2. And for the other leg, let's label that h. Or no, let's label it b. I was going to use h for height, but let's use b because it's one of the legs. So legs would be a and b. Now, the Pythagorean theorem says that the legs squared and added together, so that would be those two legs, each squared, added together, has to equal the hypotenuse squared, which is the x here. And now I can solve that for b. So we have 1/4 x squared plus b squared equals x squared. Subtract the 1/4 x squared and we get b squared is 3/4 x squared. Square root both sides and we get b is going to be the square root of 3 over 2 times x. So now we can do things like, let's split this into two segments here. Let's do the sine of 30 degrees. 30 degrees is this angle on the top. So from the top, opposite is going to be the x over 2. And hypotenuse is going to be x. So x over 2 divided by x simplifies to 1/2. So the sine of 30 degrees is actually equal to 1/2, exactly. And you can check that on a calculator, by the way. If you're in degree mode, which we currently are, you can do sine of 30, 0.5, exactly. Cosine of 30 degrees, on the other hand, is going to be, from the 30 degree angle, the adjacent side is b, which we know is the square root of 3 over 2 times x, and then divide by the hypotenuse, which is x. X is cancel, and that square root of 3 over 2 is the exact value of the cosine of 30 degrees. And then lastly, you can do the tangent of 30 degrees and do opposite over adjacent, so that would be our x over 2 divided by the square root of 3 over 2 times x. X's are going to cancel, 1/2s cancel, and then you get 1 over the square root of 3, which can also be written as square root of 3 over 3. And that's the exact value of the tangent. So there's a little bit of algebra in there, but you can, if you'd like, I ran out of space, but if you'd like, go take that and confirm for yourself. X's cancel, 1/2s cancel, 1 over the square root of 3 is square root of 3 over 3. Now, if you do the same type of thing with 60 degrees, you can do sine of 60 degrees. You'll find that things work out differently, but it's sort of like an inverse of 30 degrees. So the sine value ends up being root 3 over 2. The cosine value of 60 degrees is 1/2. And the tangent value of 60 degrees, instead of, from the 60 degree angle, opposite and adjacent are essentially swapped. So you get root 3 over 2x divided by 1/2, and this just equals the square root of 3 directly, rather than its reciprocal. So there you go. That pretty much sums it up for the exact trig values for these specific angles.